My name is Alejandro Morel. Today, as Sam said, we have the third and last seminar about indoor lighting. We're gonna analyze the calculation of energy saving measures for indoor lighting. This means how do we calculate any energy savings, money savings, environmental savings, and profitability in indoor lighting projects. Okay, so first we're going to see a quick summary of the energy saving measures for indoor lighting. Then I'm going to show the methodology. It's an easy methodology to quantify the savings. And finally, we're studying a real case. We're analyzing the measures with an example in a real building, in an hotel. We're going to follow this example from the beginning. This would be the data collection to the end, to the final results of the lighting energy audit. Okay. In last session, I commented that there are only two ways we can reduce the energy consumption in lighting. Based on this formula, based on the lighting formula, or we can reduce the energy consumption by reducing the power, the system power, or reducing the time of use. We also said that for decreasing the power, the first option is analyze the lighting level, what we call the illuminance, the lighting level in the work surface. If this lighting level is too high, there is a way we can reduce the energy consumption, that is to reduce the illuminance, the lighting level. Also, we can improve the system efficiency. We can maintain the illuminance, but improve the efficiency. The efficiency of the luminaire, the efficiency of the lamp, the efficiency even of the auxiliary equipment. And the other group of measures, the other possibility, is to reduce the time of use. We can get this with intelligent control systems, such as occupancy control, daylight control, etc. Okay, so the methodology, as I said, is really simple. If we work with the same formula, we say that consumption is the power times the time of use. So the energy saving would be the consumption 1, we call consumption 1 the consumption before the energy measures, minus the consumption 2, the consumption after the energy measures. So we have here, excuse me for a second, we have here that the consumption 1 equals power 1 times the time of use 1, and the same for consumption 2. So the energy saving would be consumption 1 minus consumption 2, or power 1 times time 1 minus power 2 times time 2. Okay, usually one of these variables, the time or the power, remains constant or can remain constant. So if the time remains constant, if we only attack the power, we use the formula we see in the top of the slide. The energy saving is the time that remains constant times power 1, the power before the energy saving actions, minus power 2. And exactly the same if the power remains constant. The energy saving is the power times time 1 minus time 2. This used to be the most useful ways, but right now, almost every energy saving project, we attack the power and also the time. So we use the first formula. Power 1 times time 1 minus power 2 times time 2. This would happen if we imply a measure that attacks the power, like lamp substitution, and also a measure that attacks the time, that reduces the time, such a detector. So almost in every situation, we're going to use this formula. But let's see an example. Okay, one of the possibilities in power reduction, we saw this in last webinar, is the substitution of an incandescent lamp by a LED lamp. We can see this in the top of the slide. This table, we can see in this table how we change a 60 watts lamp, incandescent lamp, by a 10 watts LED lamp. And we have to set the time of use. Here, the time of use is 7 hours a day, 6 days a week, 52 weeks a year. So based on our known formula, consumption equals power times time of use. We have first the starting point, where we have 60 watts and 2,184 hours. This number is 7 times 6 days a week times 52 weeks a year. And as you can see, here this number stays constant because here we are only attacking the power. In the final point, we have the same time but different power, 10 watts. Our power is 10 watts. So the energy consumption first is 60 times 2,184, here, 131 kilowatts hour. Beware of the K because we're talking about watts an hour. So when we in energy say kilowatts hour, there is 1,000 there. Okay, and the final point where we have 21.8 kilowatts hour. So the saving, as we said, is 80%, or more or less 80% is 109.2 kilowatts hour. Okay, and finally, the question, how we set this time. This is important because we can read the power, but we cannot read the time. We're going to see a little more of this in the next slide, where we have another example, but in this case, we are attacking, sorry for the arrow, we are attacking the time of use. The power remains constant. We are going to use an occupancy detector, as we see it here. So the power remains constant, 60 watts. Initially, we have 7 hours a day, 6 days a week, 52 weeks a year, such as in the other slide. So the starting point consumption is the same, 60 watts times 2,184 hours a year. But in the final point, we have this same 60 watts, but only 936 hours. This is 3 hours a day times 6 days a week times 52 weeks a year. So the final point consumption is 56.616, and the saving is 74.88. Okay, in this case, the time set is even more important because we have to set 2 times, the time before the occupancy detector and the time after the occupancy detector. So we usually set this time by measurements, by observation during the data collection, by interviews, or by estimation. Okay, moving on with the methodology, we have seen the energy savings calculation methodology. One, we know the energy saving. We can calculate the economic savings. The economic savings, and we can see in this first formula, is energy saving in kilowatts hour times the price of supply. Here we have in euros divided euros per kilowatt hour. And we can or cannot consider the replacement cost. Sometimes we consider it, sometimes we don't. We're gonna study this with further detail later. The environmental savings, we usually call the environmental savings the kilos of carbon dioxide, of CO2, we don't emit to the atmosphere. So the environmental saving in kilos of CO2 would be the energy saving in kilowatts hour times the CO2 emission factor. The investment, the cost, we just have to know the number of equipments, the number of lamps, the number of luminaries, times the price of the unitary equipment, and we have to consider the price of the installation, the manpower. And finally, the profitability. We usually use the simple payback period. Simple because we don't consider any evolution, increase or decrease in the cost of the energy. The payback period, the time in what we get our money back, would be the investment divided by the economic saving. Okay, we were just talking about the replacement cost. Sorry for the arrow again. We're talking about the replacement cost. How do we consider replacement cost, replacement savings? We have to consider first the time of use. Second, the cost of the lamps. Third, the cost, the manpower cost. Let's see an example. If we see this table over here, we have some inputs. We are going to change a fluorescent system, fluorescent lamps, by a LED system. We have 200 luminaires, and the lifespan, the lifetime of the lamps for fluorescents is 12,000 hours. For LEDs, around 50,000 hours. The time of use in this particular installation is 3,000 hours a year. And the unitary cost of the lamp, of the luminaire here, would be 4 euros for the fluorescent, 15 euros for LEDs, for one LED. And we're going to consider also the manpower cost, 15 euros an hour. And the time and the replacement time is 0.12 hours. Okay, with these inputs, we calculate that the duration of the lamps is 4 years for fluorescent and almost 17 years, 16.7 years for LEDs. This is the main problem with replacement cost, because we are saying that in 17 years from now, LEDs are going to cost 15 euros. We cannot know this. This is impossible. We cannot know this. So in many times, you're going to see that in energy audits, they just don't consider replacement cost. But if we do consider it, the replacement cost would be higher in LEDs than in fluorescent, because the lamp is more expensive. We have 3,360 versus 1,160. But if we consider the replacement cost per year, the LED is cheaper, 202 versus 290. So the savings in replacement are around 30%. This is caused because the lifespan of the LEDs is much higher than fluorescent lamps. Okay, but what if we are an Esco? If we're an Esco and the time of the contract is set, this is really, the situation, the scenario is really different, because we usually choose this duration considering lamps lifetime. We have the same inputs, but the results are really different. We have 4 years the duration of the fluorescent and 16.7 years the duration of LEDs. But we choose a duration of the contract, of the Esco contract, in 15 years. So in these 15 years, we're going to change the fluorescent 3 times, or we would change the fluorescent 3 times, but we don't change LEDs once. So the total cost for LED is 0, and the savings are 100%. Okay, always when we are designing an Esco, from the Esco point of view, of course, we are going to set a duration slightly lower than the lamp's lifespan. Okay. And moving forward, we're going to see the case study. This is a real case, an energy audit in a hotel. And as I said, we're going to go from the beginning, the data collection, to the final results, the energy saving results, economic savings, etc. Okay. The first step for every energy audit is the on-site data collection. This is mandatory if we want to do a good work. We must visit the installation. Here is, we have some data we have collected in this installation. We have the price of supply is 11 cents, and we have the CO2 emission factor is 0.38 kilos of CO2 per kilowatt hour. Okay, and we have to consider any other relevant variables that can affect the consumption. Here we have the auto occupancy. Every month of the year, we can see that the occupancy in winter is lower, 70%. In summer, in European summer, is much higher. We have 100% in July and August. And here we have the lighting inventory. When we do a lighting inventory, we have to take this data, at least this data, the room, the type of lamp, the number of luminaires, the number of lamps per luminaire, the lamp power, the auxiliary equipment in every lamp, the auxiliary equipment power, and the time of use. We need to collect this data for every lamp, for every group of lamps in the hotel, in the installation. Here we're going to study two lamps. We have selected 2 rooms in which we propose energy efficiency actions. The halls, where we have fluorescent lamps here, and the double room lobby, the rooms where we have halogen lamps. Okay, our first measure is in the rooms. We're going to replace halogen with LED in rooms. So here we have the inputs. We have the double room lobby. This is the room. We have 550 luminaires and only 1 lamp per luminaire. The power of the lamp is 50 watts of the current lamp, and these lamps have not auxiliary equipment. They don't require auxiliary equipment, so we are only consider the 50 watts of the lamp. The time of use is 3 hours a day. In this case, this is an estimation. This is an estimation that the rooms are used, the light of the rooms, 3 hours a day. And the days per year, 307.7. This is based in auto occupancy. So the new power is 10 watts. Is the LED power equivalent to the 50 watts of the halogen lamps. The cost of the new lamp is 19.49 euros. And we can add the waste management tax. It's 0.25 euros, 25 cents. But I think in these results, we have not considered this waste management tax, but we should. It's better to use it. Okay, and we have also have a replacement cost. But in this hotel, the new lamps are installed by the hotel maintenance staff. So in this case, we do not consider manpower cost. We're only considering the material cost. So the results we can see in this table at the right of the slide. The initial consumption, remember always, this is just power times time of use. So we have the number of luminaires and the power per luminaire times the time of use. The time of use a day, 3 hours a day, and the days a year, 307. So the initial consumption is 25,385 kilowatts a year, and the final consumption is 5,077 kilowatts a year, kilowatts hour a year. Sorry. So the energy saving again is 80%, 28,000 kilowatts hour, and the money saving is 2,234 euros a year. The cost, we consider the number of lamps and the cost, the unitary cost. So we have a cost of 10,720 euros. So the payback, the simple payback is 4.8 years. Okay. The second example, as we said, is for the halls, is the halls lighting retrofit, and we are going to study the possibilities in these rooms. Here, we're going to consider different saving actions. First, we're going to evaluate the lighting level. We're going to evaluate also the system replacement to improve the system efficiency. And we're going to study the control systems, the possibility of occupancy sensors and also sunlight sensors. Okay. First, we measure the luminance to see if it's correct, if it's right. We measure the luminance, as we said, with a luxometer. And we compare this value with the recommended by the UN, the UNEN 124641. Okay, the way we use the illuminance, we're going to use the average illuminance in the room. So we measure under every lamp and also between the lamps as is shown in this graph. where the yellow points are the lamps and the black points are all the measurements. Okay, here we have an average illuminance of 530 luxes compared with the 500 luxes of recommended illuminance. So in conclusion, the illuminance is adequate, so we maintain it. Okay, well, another thing about that, we have to measure the light level, the illuminance, in the work surface. So here, if the activity is writing, reading, data processing, we're going to measure on the table, not on the floor. Okay, so the second possibility is to improve the system efficiency. We're going to replace the system, and we find two alternatives, the lamp substitution or the luminaire substitution. So first, how do we decide which one? The lamp substitution is cheaper, but luminaire substitution have some advantages like better luminaire performance, the light distribution or the heat dissipation. What we're going to do, we're going to study both options with further detail so we can have more information before we can make a decision. In the next slide here, so, okay. Here we have the current situation. As we said, we have fluorescent lamps and the two alternatives, lamps replacement, luminaire replacement. Okay, first, the technology, we have, as we said, fluorescent, and the technology in both alternatives is LED. We have 180 luminaires. Currently, we have 4 lamps per luminaire, and if we change the lamp, the first alternative, we change the lamp, we maintain 4 lamps per luminaire, but if we change the luminaire, we only have a one LED panel, so we have only 1 lamp per luminaire. The current power of the lamp, the fluorescent, is 18 watts. The LED retrofit replacement is 10 watts. And the luminaire replacement is 31 watts. It's higher, but remember, we have only 1. And the auxiliary equipment power right now is 5 watts. And with LEDs, we don't consider it because we consider it within this 10 watts or 31 watts. The time of use in hours per year is 3,600 right now, and to evaluate this measure, we're not going to change it. We're going to maintain 3,600 hours a year. Okay, so the results, the consumption is almost 60,000 kilowatts hour a year, and with the lamps replacement, the savings is, consumption is 25,000, almost 26,000, and with the luminaire replacement, 20,000 kilowatts hour. Okay, we can see the energy saving is slightly higher in the luminaire replacement, 39 versus 33, 66% of the current consumption versus 57%, and also the money saving, 4,348 euros versus 3,707 euros. Okay, the unitary cost, the cost of the lamp, is 16 euros in every lamp in the first alternative, and 103 euros in every luminaire in the luminaire replacement. As we said, in this case, we're not considering manpower cost, only material cost. So the total cost is 11,000 in lamps replacement and 18,000 in luminaire replacement. So we can see that the lamps replacement is more profitable. If we decide by this, by profitability, we should choose the first alternative, the lamps replacement. Okay. And we're also studying the occupancy and sunlight detectors in the halls. Well, first considerations, we're going to analyze the lamps closer to the window and the rest of the lamps. Okay, the lamps closer to the windows, we're going to control the light with occupancy and also sunlight detectors. These lamps in this situation, in this hotel, represent 20% of the luminaires, and the 80% are not so close to the window, so we are only considering occupancy detectors. Always is important setting the time of use of the lamps. As I said, unlike the power, we can just read it. This is especially important when we study control measures because, as I said, we have to set 2 times, the time of use before the measures and the time of use after the measures. There are some equipments that measure the time of use of the lamps, and we can use it to help us setting the time. In example, we can measure in a certain room for a week how many hours the lights have been on. Even we can measure if the room was occupied. This is very helpful in Esco projects. In energy audits, we can use this, but it's really common that we just estimate the time of use. We estimate the current time of use by, as I said, observation during the inventory, by interviews, and we consider a reduction based on the building, the technology, our experience, etc. Okay, here we're going to consider that with the occupancy detectors, we're going to reduce the time of use in 25% of the hours. With lighting detectors, we're going to reduce the time of use in 20% of the hours. And finally, if we combine occupancy and lighting detectors, we're going to reduce the time of use in 40% of the hours. So here we have the results for this measure, the current situation, and the situation with the detectors. Here, remember, we don't change the lamps, just install detectors to reduce the time of use of the lamps. So the technology is fluorescent before and after the measure. We have 180 luminaires. First of all, this note, if we install the detectors, we can have a problem because fluorescent can suffer when are frequently switched on and off, and the lifetime is reduced. The consumption is not higher, but the lifetime is reduced. So we should use a special auxiliary equipment that is prepared for frequent switches on and off. Well, the power of the lamp is the same, 18 watts, and the auxiliary equipment, in this case, is also the same. What we change here is the time of use. Initially, we have 3,600 hours, and for the 20% lamps closer to the windows, we're going to get, after the measure, 2,160 hours, and for the rest of the lamps, the 80% of the lamps, 2,700 hours, because in this 80%, we only use occupancy detectors. So the energy consumption with our formula right now is 59,616, and after the measure is 42,924. The energy saving is the first minus the second, 16,692. This is an energy saving of 28%. The money saving, we just use the cost of the energy. We said 11 cents. So it's 1,836 euros a year. The unitary cost of a detector, occupancy detector, or a combined occupancy and sunlight detector is 55 euros. And we're considering to install one detector per every 6 luminaires. So here we have 180 luminaires, and we're going to install 30 detectors. So the total investment, the total cost, is 1,650 euros. As you can see, this is a really profitable investment because we're getting a saving of 1,800 euros a year, and the cost is lower. So in less than a year, we have our payback. Okay, but remember, we are here only considering the cost of the material, not the manpower. Okay, so both actions, the system replacement and also the detectors are economically interesting. So we're going to combine them. In this table, we can see the results of the combination. We have the current situation, the LED, so the change of the fluorescent for LED. Remember, we are going to change the lamps, not the luminaires. The detectors, and the combination of both, LED plus detectors. Okay, what we have to take into account here is that the total savings are lower than the addition of the unitary savings. If we see, we have the energy saving of 57% for LEDs, for LED change, of 28% for the detectors, and the total savings is 69%. If you add 57 and 28, the addition is higher than 69. Okay, the total saving is lower than the addition of unitary savings. This is called cross-sell effects. And the cross-sell effects happen always when we apply two or more saving actions in the same group of lamps. Okay, we call cross effects to this fact, the fact that the total savings are lower than the addition of the unitary savings. Okay, this happened with the energy saving in kilowatts hour, with the energy saving in percentage, and with the money saving. This doesn't happen with the cost. Okay, the cost, we can add the LED cost and the detector cost, and we have the total cost. Okay, so the payback of LEDs is 3.2 years. For the detectors, we said less than a year, 0.9 years, and with the two actions combined, we have a total cost of 13,000 euros and a money saving of 4,505 euros. So the payback is in 3 years. Okay. And finally, we're going to add both rooms. The rooms and also the halls. Here we have the results we have seen for the rooms when we changed halogens by LEDs, and the halls when we changed fluorescent by LEDs and also install detectors. The energy saving for the rooms is 20,000, for halls 40,000, combined 61. Here we can add them up. Okay, cross effects only happen when we apply two or more actions in the same lamps, in the same group of lamps. Here we are talking about different rooms of the hotel. So here we can add the savings. Okay. First, we had a payback for the rooms. We had a payback of almost 5 years. In the halls, we have a payback of 3 years. Both actions combined, we have economic and money saving of 6,739 euros a year, a cost of 24,000 euros. So the payback is 3.6 years. Okay, and here we can talk also about the CO2 reduction, what we call environmental savings. The environmental savings are all 23 tons of CO2 a year. Okay, this would be the final results for the part of the hotel I am analyzing. Okay, and a couple of considerations. First, about the economic savings. Okay, most of electric markets consider some fixed costs. Okay, we don't only have variable costs, a cost that goes with the energy, but we have also a fixed cost. Okay, as an example, in Colombia, the energy is cheaper than in Spain. But in Colombia, all the electric cost, all the electric energy cost is variable. It goes with the energy. While in Spain, some part of the cost is fixed. It depends on the power contracted. It doesn't depend on the consumption. In conclusion, being more expensive, the energy in Spain, energy efficiency actions are more profitable in Colombia. So we have to take into account not only the energy costs, but also the fixed costs. Let's see an example here. We have in this table the system. This system, we have a power cost of 55 euros per kilowatt per month, and an energy cost, as we said, as we have seen, of 11 cents. We also have another cost, such as taxes, the meter, the reactive energy, but we're only considering these two, the power and the energy. So we have a contracted power of 300 kilowatts and an energy consumption of 612,000 kilowatts hour. The power cost would be 300 times 5 times 12 months a year. So it's 80,000 euros a year. And the energy cost is 612,000 times 11 cents. So it's 85,320 euros a year. Excuse me, sorry. It's 67,320 euros. This 85,000 is the total cost, and the final is the unitary cost. So the total cost divided by the energy consumption. After we have implanted the measures, we reduce the energy consumption, but we don't reduce the contracted power. So the power cost is the same, and the energy cost is lower, 67 versus 60. The total cost is reduced, but if you see the last number, the unitary cost is higher. We have a more expensive system because the energy consumption is lower, but the contracted power is the same. If we want to reduce even more our payments to the electrical company, we can reduce our contracted power. We consider that with these measures, we can reduce our power demand in 25 kilowatts. So we reduce, if we can, if our system allows it, we reduce our contracted power. So instead of 300, it's 275. The energy consumption is the same. The power cost is lower, 16,500 versus 18,000. The energy cost is the same. The total cost is lower, and the unitary cost is also lower. Okay? And finally, the profitability. We can sell these projects, these energy saving in lighting projects, in different ways. We can sell it environmentally, as we saw. There is a reduction of 23 tons of CO2 a year. We can sell them as a technology retrofit, but we can sell them also as a profitable investment. Okay, to assess the profitability, we usually use the internal rate of return, the IRR, which as you know, is the rate that makes the net present value equal 0. In this context, in energy efficiency project, we usually consider a good investment when the IRR is higher than 12%. So here, we are getting IRR of 23%, so we can consider that this is a really good investment. Here, we are not considering financing costs. This would be only the project. If we consider the financing cost, the IRR maybe is even higher. So we can consider and we can sell this project just like an interesting investment, like a profitable investment. Okay? So this is all. I hope you enjoyed the webinar. I'm waiting for the questions.